Hello, welcome back to Decaf-Math. So today let's try some practice problems for convergence tests. This video was requested, so hello to the person who requested it, and I hope that this is everything that you hoped it would be, plus some extra sugar and spice and everything nice. So I encourage you to pause after each question to give them a try if you are trying to review this stuff or learn this stuff. But you can also just kind of keep the video running and let me kind of ramble in the background as you work through it. And we can just kind of compare notes. Hopefully you can just use this as more of a diagnostic for yourself, to see if there are any specific convergence tests that you want to review or work on. And yeah, don't worry too much about if you're getting them right or wrong though, okay? Okay, so let's see here. I made up these questions, so of course I drew inspiration from common types of problems, but I'm not saying that these problems don't exist somewhere, but I pretty much just kind of swapped around some numbers and kind of peeked at different books and stuff, so hopefully it's helpful and pretty representative. So number one, let's see here. 3 to the n over 5 to the n plus 1 for n equals 1 to infinity. So the question is, does this converge or diverge? Diverge just means it doesn't converge. So does this converge or diverge? And if it converges, what test or tests would you use? And sometimes there's not just one answer, so as long as you can sufficiently convince yourself and whoever else that your test works, then you're fine. Okay, so what's your justification? So 3 to the n over 5 to the n plus 1. Feel free to give this a try. And while we're at it, someone had actually asked about this sigma. So this thingy is sigma, and capital sigma actually, and it means the sum. So this bottom thing, this is like our index, but this tells me I'm going from 1 to infinity. So 1, 2, 3, 4, 5, ... to infinity, and I'm plugging in those values here into this thing. And then the sigma tells me I am adding them together. And that's what a series is. Series are about adding. So, but it doesn't always have to be infinity. It can be something like, from I equals 1 to 5 of I. So this was the thing that tells us what we're plugging into. So I equals 1. So 1 plus plugging in 2 plus 3 plus 4. And then this is my stopping point, so plus 5. So this is 1 plus 2 plus 3 plus 4 plus 5. Okay, so that's just for this person who is a different person actually, but who asked about sigma. So there you go. But this is for infinite series. So we're asking if this sum converges or diverges. Okay, so hopefully you got a minute there to work this out, or at least give it a go. But like I said, pause if you want more time. One thing that I see is that this 3n over 5 to the n plus 1, that term is, or for any n really, is always going to be less than 3 to the n over 5 to the n because of this 5 to the n plus 1, right? So that's always bigger than 5 to the n, because any number, and then you add 1 to it, it's going to be bigger. And since it's on the denominator, on the bottom of this fraction, that makes a bigger denominator, means a smaller fraction, with everything else held equal, right? So that means this is true for all n. That's for all n, meaning that this sum is always going to be less than this sum, this 3 to the n over 5 to the n. And I can actually rewrite this as 3 over 5 to the n, right? That's just our rules for exponents. And this sum is actually a geometric series. Geometric series. Because if I just write out, the first few terms of this, I plug in n equals 1, so 3 over 5. Then my sigma tells me I'm adding. If I plug in 2, it's 3 over 5 squared, so 9 over 25. 3 over 5 cubed, so 27 over 125 plus dot dot dot. And the important thing to note here is just that I'm always multiplying by another 3 over 5, right? That's just kind of how exponents work anyways. Plug in 1, plug in 2 is 3 over 5 squared, multiply another 3 over 5, then I get 3 over 5 cubed, right? So my r is 3 over 5. That's what I'm multiplying between terms. And since that value is less than 1, or the absolute value of it for the negative case, in this case it doesn't matter, but since it is less than 1, this series converges. And that's because that's just how geometric series work, right? We can actually get the exact value of the sum with our a0, so our first term divided by 1 minus that r. But we don't actually care what the value is, we just care that it converges. And the reason for that is because if this converges, so this is my geometric series, which is equal to this thingy, but we compared our original problem with that, and we showed that this series is less than this one. Each of our terms is less than 3 over 5 to the n for all n. So I can compare this with this, and since this converges, and we compared it in a way that this is always less than this one. So our problem converges by the comparison test. Converges. And it's by the comparison test. But we also needed to compare it with something that we knew would converge if we were going to try and show that, and that's just to know that geometric series is where r is less than 1 converge. So, comparison test, very nice, and it converges, yes. Okay, very nice. So let's move on to number 2. Number 2. How about 2n squared minus 1 over n squared plus n? What do you think? Does this converge or diverge? And if it converges, what test would we use? So, did I trick you here? Or did you see it? This actually diverges, and it's because in the back of our minds we can always try out this limit. So, the limit of our thingy, if it does not equal 0, then we automatically know that our thing diverges. Okay? If it equals 0, if this limit equals 0, it doesn't mean anything. So it doesn't necessarily mean that it converges. We just know that if it's not equal to 0, that it diverges. So we can go ahead and try out this limit. We can see that as n approaches infinity, that this limit goes to 2, just because when n gets really, really big, this falls away, 2n squared divided by n squared is 2. But of course, if we want to write that limit out rigorously, we can kind of, we can divide by each term by n squared by the largest exponent, the largest degree, and so we're just dividing by n squared on the top and the bottom, but then we have to distribute that, so that just means every term. So 2 minus 1 over n squared and 1 plus 1 over n, and this is just for those of you who want to write out the limit more rigorously. But then we can distribute this limit part, so minus the limit as n approaches infinity, but the limit for 1 over n to the any power, so n to the k, that whole thing goes to 0, and this goes to 0. So 2 over 1 is 2. So however you want to convince yourself that the limit of this thingy is 2, that's just up to you. But the part that's important is that 2 is not equal to 0. Unless we are talking about our silly math that we've done recently. But 2 is not equal to 0, which means that this actually automatically diverges. Okay, so this actually diverges. And we like this because when the limit's not equal to 0, we don't have to do any of our convergence tests. So that's I think that's the first thing that we should sort of check, is if it's obvious that the limit is not 0, or if there's a way to kind of look at it in the back of your mind, if it's not too much work to show yourself that the limit's not 0, then go ahead and start with that, because then we can just say that it diverges right off the bat. Okay? Okay. Next. Okay, so next try this one. N over n cubed plus n from 1 to infinity. That's an n cubed plus n, so an n divided by n cubed plus n. So give that one a little go. So the first thing that I notice is that there's an n in each of these terms, so I can just use some algebra to get rid of that. And we don't have to worry about dividing by 0 because n is from 1 to infinity. So I can just kind of divide by n on the top and bottom. That also means we have to distribute that. So 1 over n squared plus 1, right? Just getting rid of an n in each of those terms. And then I'm kind of seeing a comparison test again, but I kind of have to know that each of these terms, kind of like in our very first question, this is going to always be less than 1 over n squared, because it's the n squared plus 1, right? And so it's less than this, but then the question is, does this thingy, whoa, wow. That's a less than sign. So this is less than. So the question is, does this thing converge? Because if we know this is less than this, but then this thing converges, then this thing also converges. So this does converge because this is a p-series test, or we can use the p-series test rather. It's 1 over n to the p, where p here is 2, and 2 is greater than 1. And since it's greater than 1, by the p-series test, this thing converges, and by the comparison test, therefore, our original thing converges as well. So this, our question, which I kind of wrote all over, so I'll just write back our original problem, n over n cubed plus n. This thing converges, and we used here, but you might have done it a different way, the comparison test, but also the p-series test. Nice. So converges, and we used these two. Cool. Okay, let's try another. Let's try from 1 to infinity. How about 2n over 1 plus 7n all to the n? 2n over 1 plus 7n all to the n. Give that a go. Straight away, I see this exponent of n, so that makes me think that I will try the root test. The root test. So that just means if I take the limit as n approaches infinity of my nth root of this thing, the absolute value of this thing if it happened to be negative, but this is going to be positive. But if I take the nth root, and I take take this limit. So I can either write that as literally the nth root of my thing, so that these cancel, right? Or you can think of the nth root as being raised to the power of 1 over n, right? But either way, the nth root gets rid of this n exponent. So this would be the limit as n approaches infinity of just my 2n over 1 plus 7n. And you would take the absolute value here. Okay. And the limit as n approaches infinity of this thing is 2 over 7. Just because that one goes away, and you can again divide each term by n if you want to write that limit out. But as n gets really, really large, these two are what matter, and so 2 over 7 is what's left. And this number is less than 1, therefore our sum converges. And if this number were greater than 1, then it diverges. Okay, so this converges by the root test. Root test. Nice. And usually if I have like an nth thing like that, the root test is nice because you can just get rid of that exponent. Nice. So let's try one more. One last one for now. Let's try n equals 1 to infinity n plus 5 factorial over 2n factorial. So let's give this a try. I like factorials because we can use the ratio test a lot of the time, not all the time, and there of course may be other ways to do this, but with the ratio test we are basically going to take the limit as n approaches infinity, and we set up the ratio of a of n plus 1 divided by a of n. And when it comes to factorials, we can use a lot of the properties. When you divide factorials, things tend to cancel, such as n plus 1 factorial over n factorial. That's like if we were to do 6 factorial over 5 factorial, because n plus 1 is 5 plus 1, right? If you were to write out the factorial here, 6 times 5 times 4 times 3 times 2 times 1 over then 5 times 4 times 3 times 2 times 1, it all cancels except the 6. So when you divide factorials that are kind of in a sequence like that, a lot of stuff cancels out. So you can kind of use this thinking when you set up this ratio. So I'm gonna kind of try out the ratio test and take the limit as n approaches infinity of the absolute value of this a n plus 1 over a n. So a n is just my term, just my whole, like my original thing. So n plus 5 factorial over 2n factorial. And my a n plus 1 is just if I plugged in the next term, so n plus 1. So that would be n plus 1 plus 5 factorial over 2 times n plus 1 factorial. I'm going a little parentheses happy here, but just because I want to be clear with what thing factorial, because without that it might look like 5 factorial or whatever, right? So you want to make sure it's the whole thing factorial. So this looks messy, but we can still use properties of factorials like we said and just work a little bit of algebra here. So since we have a fraction divided by another fraction, I can just multiply by the reciprocal of the bottom. So the limit as n approaches infinity of this thingy, so n plus 1 plus 5, we can just get rid of those parentheses, so just n plus 6 factorial over 2n plus 2 factorial, just distributing that 2, times, and then flipping this bottom, so 2n factorial over n plus 5 factorial. Okay, cool. So now this is where a bunch of things can cancel, I think, right? So n plus 5 factorial can cancel with this n plus 6 factorial and leave an n plus 6, because this would be n plus 6 times n plus 5 times n plus 4 plus dot 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 times n minus 1 and minus 2, right? Dot dot dot. So everything past the n plus 5 cancel, because you can cross multiply. And same for this and this. This can completely go away, and this would leave you with 2n plus 2 times 2n plus 1, right? And then you would have a 2n, but that would cancel out with everything before this. So this is kind of nice. You have limit as n approaches infinity of n plus 6 over this thingy, 2n plus 2 times 2n plus 1, which you can FOIL. I'll write it out here. We can FOIL that out. We don't have to care about every term here, actually. We only care about the highest power, but we might as well. So we have 4n squared plus 2n plus 4n, so plus 6n, I believe, plus 2. Hopefully that's right. 4n squared plus 2n plus 4n, that's 6n plus 2. Yep, I think. And so when we take the limit as n approaches infinity, we're taking the absolute value here. We have, let's see, so of course you can still do that thing where we divide by the highest exponent, so n squared in this case, but you can also just notice that when n gets really large, this goes away, these terms go away, you have this thing going on, so you have a 1 over n, right? So this would be the same as n approaches infinity of 1 over 4n, because the bottom has a 4n squared and the top has just an n, so that means this limit goes to 0, and we don't need the absolute value in this case because we're taking as n approaches positive infinity. So all that being said, this ratio thing gives me that limit of that ratio is 0, which is less than 1. So our problem converges by the ratio test. The ratio test. Nice. Okay, cool. Oof, it seems like a lot. Maybe it's just because the problem that I made up are the numbers that are just kind of weird, but oh well. It's still not too bad, right? You just have to be familiar with factorials. Sometimes they're just nicer and more things cancel. but whoops, this is what I picked. And yeah, I think that's it for now. I had an example of the integral test, or at least I think what would be the integral test, but I just realized that we actually, okay, so I should write that out for the integral test. I think I'll do a separate video for that integral test, because for the integral test it's a little more complicated to show. You have to, there are conditions for it to work, and you have to show that your series or your function is positive and continuous and decreasing on your interval. And so the problem that I had is a little more tedious to show that. And even if those are all true, you still have to actually take the integral of your function. And so if you want to give it a try, you're welcome to. I'll write it here, but I'll probably work it out in another video, okay? So ne to the negative n squared, n equals 1 to infinity. So I'll tell you, I'm pretty sure this one converges by the integral test, but like I said, you have to confirm that these are actually true. So this is positive because we're going from 1 to infinity, and so that makes n positive, and e to the power of anything is positive, so that's fine. It's continuous, and that's pretty straightforward as well, right? There are no, like, nothing really breaks here. But decreasing, you have to show that this is decreasing for x greater than 1, and I say x because we end up taking the integral from 1 to infinity of, I'm just replacing all the n's with x's, so x e to the negative x squared. So to show that that's decreasing for x greater or equal to 1, you can either just graph it and show yourself that that's true, but to actually show that, you have to take the derivative and show that that derivative is less than 0 always for x greater or equal to 1, because if f prime is less than 0, f is decreasing, right? And that derivative might get kind of messy. You have to use the product rule and the chain rule here, so bleh. And then even once you do show that the conditions are true, you have to actually find this integral. But I did want to just point out here, since we are reviewing a little bit, that one thing that makes me think that I'll use the integral test is that I have like a n squared thing going on, a negative n squared, and I have like an n here, which the derivative of negative n squared is negative 2n, so I have like an n term here, so that makes me think a nice pretty u substitution would come in handy, but I haven't actually worked this out, but you can kind of either plug this into a calculator or something and see if this integral, if this tells you anything from the integral test. So basically, if this is the number, if it actually converges to something, then our function, this series, converges. So I think this does. I think we could just use some u substitution, but we'll work this out, okay? But I just wanted to point that out. So the integral test is really when it seems like, well, one, taking the integral is not too bad, but two, you have to actually, the thing is that you have to also show that these are true, and sometimes the problems aren't quite so yucky like this. Sometimes the integral is a little bit nicer, but still, this is doable. So that's kind of what made me think that we would use the integral test, but I wonder if there are any other tests that we could do, like comparing this with something. Not really sure. But anyways, I hope that these problems were helpful. I don't know where. Oh, here they are. Remind me to come back to this one if you're interested in it, but I'll hold off for that for now. But I hope this little review was nice and helpful. We can always come back to this in a little more depth. I'll see if I can dig out more questions or something. Like I said, this has been a while for me too, so anyways, thanks for joining